The smell of molten steel and burning oil clung to the air like a second skin. Sparks flew from the welding stations in irregular arcs, each one leaving a faint silver trail in the heavy fluorescent-lit hall. The roar of machinery was constant, punctuated by the hammering of rivets and the whine of overhead cranes shifting hull plates into place. It was a sound that never stopped, not for lunch, not for prayer, not even for exhaustion. William Bill Karlsen wiped the sweat from his brow and squinted at the seam he had been fussing with for the past hour. The M4 Sherman hull section before him had been rejected twice for microfractures along the welded plates. Karlsen ran his gloved hand along the edges, feeling the minute imperfections that others dismissed as acceptable tolerances. He frowned. The Army's ordnance specifications allowed a variance of up to 0.03 inches, but in his experience, even that could spell disaster in the Pacific Theater, where tanks often faced both artillery shells and the unpredictable humidity of jungle terrain. Karlsen was 27, with a face lined by early mornings and late nights, and hands calloused enough to leave impressions in steel. He had grown up in Dearborn, a second-generation machinist, learning the language of metal before he could properly read a book. He was quiet but deliberate, the sort who noticed the tiny things everyone else ignored. A hairline fracture in a casting, a slight discoloration from overheating, the subtle warping of a weld bead under stress. He crouched low, igniting the arc with a practiced flick. The manganese-silicon alloy he had been experimenting with hissed under the heat, and the molten bead spread across the seam like quicksilver. To anyone walking past, it was just another routine weld. But Karlsen knew what he was doing. This alloy, when applied with the correct amperage and dwell time, filled microfractures before they propagated under stress. He had seen it in test plates. He had watched it in experimental tanks he was not authorized to touch. At the far end of the hall, the foreman, Mr. Chester Van Brunt, shouted over the din. "Karlsen, don't let that spark wander into the wiring conduit." Karlsen gave a quick nod without looking up. Sparks always wandered. Sparks always fell where they shouldn't. But he had learned to control them. It was a small victory in a day of controlled chaos. The Chrysler Tank Division logbook recorded production figures with a clinical detachment. 92 hulls completed on October 7th, 1,942, with 4 rejections for weld inconsistencies. None of those rejections listed the underlying cause. Karlsen's own modifications, the alloy application, the precise bead sequencing, were absent. In the eyes of the engineers, he was nothing more than a civilian welder, a name on a badge, not a voice in the design room. He pulled back and examined his work under the harsh glare of the inspection lights. The seam was uniform. No pitting, no slag inclusions. If the Army would ever allow him to implement it, he knew these hulls could survive the kind of hits that had already destroyed Shermans in North Africa and the Solomon Islands. But the Army would not allow it. Not yet. The morning dragged on, punctuated by the rhythmic banging of the assembly line. Welders moved in a careful choreography, navigating around gantries and crane hooks, exchanging brief words with one another. Need another rod? Torque the bolts? Shift in 20. The men rarely paused for conversation. There was no time. War demanded speed, and speed, in the eyes of the bureaucrats upstairs, was more important than survival. Karlsen crouched back over the seam, cleaning the tip of his torch. He remembered the day he first proposed the manganese-silicon method to the plant engineers. They had listened politely while scribbling notes into their clipboards. "Interesting," one had said, "but unproven. Keep it on the experimental bench for now." Unproven. The word had stung. It implied not that the method lacked merit, but that it threatened the careful hierarchy of authority, a young welder's ingenuity challenging decades of institutional process. He reached for his notebook, a small leather-bound journal he kept tucked in the pocket of his overalls. Page after page contained diagrams, formulas, and observations. Arc voltage, bead thickness, tensile test results, microfracture observations under magnification. It was meticulous, obsessive, and entirely invisible to everyone except himself. He flipped to October 2nd and reread his entry. Tested 0.05-inch seam plate under stress. Manganese-silicon alloy prevented propagation. Control plate fractured within 12 seconds at 600 pounds per square inches. Could be applied to hulls if approved. Approval, however, seemed a distant fantasy. Karlsen knew the Army engineers preferred speed over innovation. They wanted tanks off the line, not experiments that might slow the production. Yet every failed hull he passed reminded him of the stakes. Men would ride inside these tanks, and the difference between a hull that cracked and one that held could mean life or death. At 11:30 a.m., a group of inspectors entered the welding bay. Clipboard holders, sharp suits, eyes that flicked from weld to weld as if they could see the steel's secrets through the air itself. Karlsen stepped aside to let them pass, feeling the weight of their scrutiny. He noticed the way they ignored his work, focusing instead on superficial uniformity. No questions about the alloy, no curiosity about the bead sequencing, just numbers, inches, percentages, compliant or rejected. The foreman approached him again, this time quieter. "Bill, I know what you're doing there. Don't take it personally. They can't see it yet." Karlsen nodded, understanding perfectly. He had learned the lesson early in his apprenticeship. Bureaucracy moves slow, even when the work at hand is urgent. Still, he allowed himself a small private satisfaction. The seam gleamed under the light, flawless. A soldier's life might one day ride upon it. That was enough for now. As the day wore on, the hall grew warmer, filled with the smell of heated metal and grease. Welding helmets lifted, sparks subsided, cranes hummed their last notes before the shift change. Karlsen finally stepped back, stretching muscles cramped from long hours in crouched positions. Outside, the autumn wind had a sharp bite, but inside the arsenal, the air was heavy with the tang of industry. In the Chrysler Tank Division logbook for October 7th, 1942, Karlsen's contributions would never appear. But in his small notebook, the experimental alloy was recorded in precise detail. In his mind, it existed as proof of a possibility the engineers could not yet see, that a welder's instinct, combined with science, could outpace the rigid lines of bureaucracy. And somewhere, far from Detroit, in the sweltering jungles of the Solomon Islands, Sherman tanks awaited their fate. Whether they burned or held their crews safe might one day depend upon a decision made here, on this ordinary October morning, in the smell of steel and oil. The morning shift began with the same mechanical rhythm that had defined the arsenal for months. Cranes whined, belts rattled, and the unmistakable smell of heated metal mixed with motor oil filled the cavernous hall. Yet this morning carried a weight beyond the ordinary. Karlsen had been summoned to the engineering office, a meeting that, by the tone of the official memorandum pinned to the time clock, promised neither praise nor recognition. The office was stark. Fluorescent lights cast sharp shadows on walls lined with schematics of the M4 Sherman, the armor thickness, engine layout, and internal hull structure, carefully annotated in pencil and ink. Karlsen stepped inside, clutching his notebook under his arm like a talisman. At the head of the long table sat Chief Engineer Harold Strathmore, a man in his 50s whose sharp eyes and tightly pressed lips betrayed both experience and suspicion. Around him were three other engineers, younger but equally precise, their pens poised to mark the margins of Karlsen's ideas with polite but dismissive notations. "Mr. Karlsen," Strathmore began, his voice crisp, "we've reviewed your proposal for the manganese-silicon weld application." He tapped a sheet of engineering notes. "While your results are interesting, they are, by ordnance standards, unverified. The Army requires proven methods. Your approach introduces variables we cannot quantify at scale." Karlsen listened, nodding, but a tight knot formed in his chest. He had anticipated this response. "Sir," he said, "I ran tests on hull plates using the standard Army tensile methods. The microfractures were eliminated. I can replicate the results on full hulls with proper supervision." Strathmore's eyes, flicked to the assistant engineers. One of them, a young man named Walter Keane, whispered something, and the others nodded. "It's not a question of replication, Mr. Karlsen," Strathmore replied. "It's about approval channels. No civilian mechanic can alter welding procedures without formal sanction. The risk to production schedules and liability is too great. Your method is rejected. For the record." Karlsen's jaw tightened. "For the record," he repeated quietly, echoing the phrase as though it were a gauntlet thrown down. He wanted to argue, to explain that every failure in North Africa and the Solomons had begun with something small, a seam, a crack, a brittle weld that the bureaucracy dismissed as inconsequential. But words would not change the forms, the checkboxes, the signatures that decided life and death in distant theatres of war. After the meeting, Karlsen returned to the welding bay, carrying not just his tools but the invisible burden of frustration. He observed the assembly line in a new light, noting the tiny imperfections that engineers would allow, the seams that would eventually carry soldiers into battle. He walked past a nearly completed Sherman, its hull gleaming but vulnerable. In his mind, he traced the microfractures that might propagate under enemy fire, each one a silent threat to the lives of men he would never meet. The rejection was logged officially that afternoon. Chrysler Tank Division logbook, October 14, 1942, recorded, "Proposal by civilian welder Karlsen reviewed, procedure unapproved. Production to continue under current standards." There was no mention of test results, of hours spent experimenting, of potential lives saved, just a line of text, sterile and absolute. But Karlsen was not ready to abandon the idea. During his lunch break, he retreated to a small alcove near the rear of the plant. The muffled roar of welding stations was distant here, replaced by the occasional clatter of passing carts. He opened his notebook and reviewed his formulas, annotations, and experimental results. He plotted stress curves against weld compositions, noting where manganese content reduced fracture propagation. The results were undeniable, yet invisible to those who judged only by paperwork. That afternoon, Karlsen attempted a small experiment in secret. Using scrap hull plates, he applied the alloy with a torch borrowed from the night shift, careful not to draw attention. Sparks flickered in controlled arcs as he traced each seam, documenting the temperature, bead formation, and cooling rate. By the time the day's shift ended, he had completed a small plate assembly for tensile testing. The next morning, he submitted it to the plant's internal materials lab. The lab technician, a burly man named Jim Rutherford, examined the plate with skepticism. "You didn't get approval for this," Rutherford said. Karlsen replied simply, "I just want to see if it works under stress." Rutherford shrugged, and the test commenced. Hydraulic presses applied incremental force, and the plate held no fractures, no propagation. The control plate, prepared with standard Army procedures, failed at 600 pounds per square inches. Karlsen watched the gauge climb, his heart beating in time with the machine. Proof, at last, tangible, indisputable. Yet even with the results in hand, he knew it would take months, perhaps years, for the method to be officially recognized. By mid-October, whispers began circulating among the line welders. They noticed Karlsen's meticulous work, the uniformity of his seams, the absence of pitting or cracking. Some asked questions. Others simply nodded, understanding that the man's obsession was rooted in something deeper than efficiency. It was survival. One afternoon, Karlsen encountered Sergeant Thomas Avery, assigned to the Ordnance Quality Assurance Team. Avery watched Karlsen's welding from a distance before approaching. "Kid," he said quietly, "I've seen your plates. If you ever get approval, you might save a lot of lives." Karlsen allowed a small, almost imperceptible smile. Encouragement from within the army hierarchy was rare. It would not change the rejection, but it lent legitimacy to his conviction. Back in the office, Strathmore updated the engineering logs, oblivious to the growing evidence. The logbook for October 16th noted, "Reinforced hull testing continues under standard welding protocol. Karlsen's alloy method remains unapproved. Production targets must be met." The text was bureaucratic, unyielding, a reminder that, In wartime, innovation was often subordinate to conformity. Yet the seeds of change had been planted. Karlsen's meticulous documentation, secret experiments, and unwavering attention to detail created a record that could not be ignored indefinitely. If the war continued to expose the vulnerabilities of the Sherman in tropical combat, someone would eventually revisit the civilian, welder's rejected method. And when that day came, the lives of countless tank crews could depend upon a single spark, a single bead of molten manganese-silicon alloy applied in a Detroit factory, far from any battlefield. As October drew to a close, Karlsen returned nightly to his alcove, welding in private, recording results, calculating stresses. The hum of the plant faded into the background, only the hiss of molten metal and the faint smell of steel and oil remained. He knew that progress, like metal, required both heat and patience, and that one day, his work, rejected for the record, might rewrite the rules of survival on the front lines. The Mediterranean sun glinted off the steel hulls of the M4 Sherman tanks as they disembarked from Liberty ships at the port of Algiers. For the men of the 339th Tank Battalion, it was their first taste of a foreign war zone, the scent of salt, diesel, and sand mixing with the tang of diesel oil from the tanks. For William Bill Karlsen, the civilian welder who had pioneered the manganese-silicon seam reinforcement, it was the moment when theory would face reality. Karlsen had arrived with the battalion under the guise of an ordnance observer. His official orders permitted him to monitor and document tank performance in combat, but they did not authorize field modifications. Still, every reinforced hull he had welded in Detroit and tested at Camp Claiborne now rumbled across the docks, each tank a rolling testament to his months of experimentation. The battalion's commander, Lieutenant Colonel Richard Harlan, had given him a measured nod. "You'll watch, Karlsen, but these are our men's lives. Any modification without approval is a risk." Karlsen simply replied, "I just want them to survive." By mid-February, the 339th was deployed to the front lines outside Tunisia, joining the build-up of American forces for the push against German and Italian positions. The terrain was a patchwork of rocky hills, olive groves, and narrow roads, a testing ground as unforgiving as any laboratory. The Shermans, relatively new and untested in combat, rolled cautiously along these routes, their engines growling over gravel and sand. The first engagement came unexpectedly. Reconnaissance reported an enemy Panzer III column moving toward a supply depot near Mejez el Bab. The battalion prepared for a defensive ambush, positioning tanks along ridgelines to maximize fire arcs. Karlsen moved among the crews, checking hull plates and observing seam joints, his eyes tracing the manganese-silicon welds that had been the subject of so much debate back in Detroit. At 15:30, the distant rumble of German armor grew louder. Panzer shells tore through shrubs and dirt, exploding near the reinforced Shermans. Karlsen noted every vibration, every minor flex in the hulls. When a 75mm round struck one Sherman squarely in the front glacis, the explosion sent a plume of smoke into the air. Soldiers held their breath. The tank shook violently, but the reinforced seams held no fractures propagated along the welds. Corporal James "Jimmy" Harris, behind the tank's turret, exhaled sharply. "If that had been the old weld, we'd have had a breach right through the hull." He patted the side of the Sherman. Others began to notice the difference. Across the ridge, two standard weld Shermans were not so fortunate. Shells pierced their armor, forcing hasty retreats and emergency repairs. Karlsen scribbled notes rapidly. Hull #3. Glacis plate impact, 75mm, angle 32 degrees. Weld intact, microfracture absent. Each entry reinforced the quiet, unofficial truth. The rejected welding method could save lives in combat. Over the next several days, the battalion encountered repeated enemy fire. German 50mm and 75mm guns tested the Sherman's limits. On narrow passes, tanks endured crossfire, anti-tank mines, and improvised roadblocks. Observers documented a consistent pattern. Standard hull Shermans suffered fractures at seams and hull junctions in 64% of direct hits, while Karlsen reinforced tanks held 92% of impacts without structural compromise. Despite the evidence, official reports remained cautious. Ordnance officers noted performance metrics in logs, but refrained from recommending wholesale adoption. Communications back to Detroit emphasized field observations only, no production adjustments. Karlsen understood the bureaucracy, but found solace in the data and the growing respect of the crews. One particularly harrowing engagement took place on February 21, near Kasserine Pass. The 339th encountered a German armor column, including Panzer II and a few Stugs. Artillery support was minimal. During the firefight, one Sherman received 2 direct hits in rapid succession. Soldiers inside braced for catastrophic failure. Smoke filled the interior, and the driver slammed the brakes instinctively. When the dust cleared, the tank remained intact, seams unbroken, and the crew emerged largely unharmed. Karlsen recorded the incident meticulously. Hull #7, dual 75mm impacts, front and side. No propagation of microfractures, crew safe. Private Ramirez, who had been transferred overseas to maintain tanks, approached Karlsen after the skirmish. "I don't know how you did it, Bill, but these tanks are holding. I've seen others crack like paper." Karlsen gave a brief smile. "Just careful welding and a little alloy trick, that's all." Ramirez shook his head in awe. "That's more than just. That's survival." News of the tank's resilience spread quietly among the Allied command in North Africa. Officers began to consult Karlsen informally, seeking insight on welding techniques, alloy composition, and reinforcement patterns. Yet no formal approval came. Karlsen remained a shadow observer, quietly proving that innovation, even when rejected by bureaucracy, could have decisive battlefield consequences. By the end of February, the 339th Tank Battalion had participated in multiple engagements along the Medjez El Bab corridor. Combat reports, compiled in situ, highlighted the stark contrast between reinforced and standard hulls. Casualty statistics indicated that crews in Karlsen-reinforced tanks were 38% less likely to suffer injury from hull breaches under similar combat conditions. At night, after battles, Karlsen would sit near a burning oil drum, reviewing notes, maps, and photographs taken by reconnaissance units. He sketched weld diagrams directly onto the margins of operational maps, hypothesizing about angles of impact, stress distribution, and reinforcement optimization. It was meticulous work, the kind of quiet persistence that often went unnoticed in the chaos of war. One night, Lieutenant Colonel Harlan approached him, looking over his sketches. "You've got the numbers," he said. "The men believe it. The brass, they're slow. But one day, they'll see it too." Nodded, aware that official recognition might never come, but understanding that results spoke louder than approval. By the time the battalion was withdrawn for refit and resupply, Karlsen had amassed a comprehensive set of field data. Hull integrity, microfracture incidents, crew survivability, and battlefield adaptability, every metric reinforced the efficacy of his rejected method. The Algerian desert, harsh and unforgiving, had become a proving ground. In his notebook, Karlsen wrote a line that would later appear in his post-war memoirs. "Innovation is measured not by approval, but by survival. These tanks, welded in secrecy and tested by fire, may be the difference between life and death on foreign soil." The sun had barely risen over the jagged hills surrounding the Mareth line when Lieutenant Colonel Richard Harlan's voice crackled over the radio. "All units, prepare for engagement. Intelligence reports Flampanzer activity near the ridge." For the men of the 339th Tank Battalion, the warning carried a unique kind of dread. Flampanzers, German-engineered tanks equipped with flamethrowers, were notorious for their ability to ignite Sherman tanks upon contact. In North Africa, a single well-placed flame could turn a 30-ton vehicle into a blazing coffin. Karlsen, reviewing his field notes, understood the stakes better than most. If his manganese-silicon welds could resist mechanical fractures, could they also withstand the sudden expansion of metal under intense heat? By mid-morning, the battalion was positioned along a narrow pass. Olive trees and jagged rocks provided partial cover, but visibility was limited. Karlsen moved among the crews, performing last-minute checks of hulls, engine compartments, and weld seams. He examined the reinforced areas along the sides and front glacis, mentally calculating heat transfer, metal expansion, and potential stress points. At 9:42, the first German vehicles appeared. 2 Flammpanzers, accompanied by Panzer III escorts, crested the ridge with mechanical precision. Flames erupted from the German tanks in a coordinated arc, targeting the Sherman line. Crews braced themselves. The heat was immediate, intense, and suffocating. Smoke, thick and acrid, filled the narrow pass. The first hit struck a standard weld Sherman. Within seconds, the tank's engine compartment ignited. Crewmen scrambled out as the hull warped, the metal groaning under thermal stress. Karlsen, notebook in hand, recorded the event. Hull Hushun 2. Standard weld, Flammpanzer impact, fire propagation immediate, crew evacuated. A reinforced Sherman, Hull H5, took the next direct flame. The fire licked along the reinforced weld seams. Karlsen watched as the metal glowed but did not fracture. The hull's integrity remained intact. Sparks and heat radiated across the surface, yet the manganese-silicon welds prevented the metal from splitting, keeping internal fuel lines from rupturing. Private Ramirez, manning the main gun, shouted over the roar, "She's holding, she's not burning." Over the next 15 minutes, multiple attacks tested the Sherman's resilience. Flammpanzers advanced, weaving streams of fire across hulls and treads. Standard weld tanks succumbed quickly. Reinforced tanks held. Karlsen documented each engagement meticulously. Hull H3, H5, H7. Flammpanzer direct flame, heat to 1,200 degrees Fahrenheit, welds intact, no fuel ignition. Lieutenant Colonel Harlan, observing from a nearby ridge, radioed down to Karlsen. "This is incredible. Your reinforcement, it's actually saving lives." Karlsen nodded, though he remained focused on observation rather than praise. His mind raced with calculations. Thermal expansion, microfracture suppression, and alloy composition, all variables that combined to create a survivable hull under flame attack. As the battle continued, German engineers adjusted tactics, attempting to target side panels and engine compartments. Karlsen's reinforced welds held firm, absorbing the mechanical and thermal stress that would have crippled other Shermans. By the end of the engagement, every standard weld tank had either caught fire or been abandoned. Every reinforced tank remained operational. After the skirmish, the battalion regrouped. Crews emerged shaken but alive. The difference in survivability was stark. Karlsen's notes, later used in the North African Combat Analysis Report, reflected a 70% reduction in fire-related casualties among reinforced tanks. It was the first empirical evidence that his welding method could render a Sherman fireproof against flamethrower attacks. That evening, in the aftermath, Karlsen walked among the tanks, inspecting the hulls with flashlight in hand. The heat of the day still radiated off the metal. Minor warping was evident, but nowhere did he find fractures or ruptures. Soldiers patted the tanks, murmuring thanks or simply shaking their heads in disbelief. Private Ramirez, leaning on Hull H5, said, quietly, "I've never seen anything like it. It's like they're invincible." Karlsen remained methodical. He measured seam temperatures, documented oxidation, and photographed metal deformation. In his notes, he recorded calculations for heat tolerance, stress distribution, and metallurgical behavior. These were later submitted, unofficially, to ordnance officers as field observations, a cautious step, intended to share data without overtly challenging existing production protocols. Meanwhile, German flamethrower tactics evolved. New angles of attack, coordinated infantry assaults, and artillery support all attempted to negate the Sherman's survivability advantage. Yet, in every instance where Karlsen reinforced tanks were hit, structural integrity held. In one particularly close encounter, Hull H7 absorbed a dual Flammpanzer and 50 mm shell assault without catastrophic failure. Crewmen reported only minor burns, largely due to external exposure rather than internal ignition. Karlsen added this entry: Hull #7. Flampanzer plus 50 mm AP. No hull breach, crew survivable. Reinforced weld confirmed effective under combined stress. At night, in temporary encampments, Karlsen held informal discussions with tank crews. He explained the science behind manganese-silicon reinforcement, illustrating how the alloy reduced microfractures and increased heat absorption. Soldiers listened, fascinated by the combination of metallurgy and battlefield practicality. Though the method remained unofficial, respect for Karlsen grew. He was no longer simply a civilian observer. He was a lifeline for men facing infernos of steel and flame. Lieutenant Colonel Harlan, in a private conversation that evening, expressed his frustration with bureaucracy. "We could save hundreds of lives if Detroit understood this. But approval will take months, maybe years. Until then, it's just us, the desert, and your welds." Karlsen replied quietly, "Then we make it count here. One tank, one crew at a time." By March 5, after repeated engagements with flampanzers, the battalion had amassed detailed comparative data. Standard welds failed under flame 85% of the time, resulting in high casualty rates. Karlsen reinforced tanks resisted fire in 90% of direct hits, with significantly reduced crew injuries. This evidence would later become central to post-war studies on tank survivability, although at the time it remained confined to field reports and Karlsen's private notebooks. In his diary, Karlsen later wrote, "We cannot control bureaucracy, nor the slow march of approval. But here, in the heat of battle, we can test, observe, and save lives. If innovation is to be judged by impact rather than acceptance, then these tanks, flawed yet reinforced, are proof. Fire may rage, shells may strike, but men walk away. That is enough for today." The Fireproof test in Tunisia marked a pivotal moment in Sherman tank development. A moment when a rejected Fireproof test and a welding trick transitioned from theory to life-saving reality. Though recognition would come years later, in the deserts of North Africa, William Karlsen's innovation had already proven itself in the crucible of war. The smell of oil and steel hung thick in the Chrysler tank arsenal, but today it was tempered by tension. William Bill Karlsen walked along the assembly lines with a clipboard, eyes scanning hulls fresh off the production floor. The hum of welding machines and the rhythmic clanging of hammers had become a familiar background symphony, yet every step carried the weight of expectation. Karlsen's manganese-silicon welds, proven in the deserts of Tunisia, had yet to gain official recognition. The problem was simple, if maddening. Bureaucracy. The Army Ordnance Department required exhaustive testing before altering the production protocol of the M4 Sherman. Engineers in Detroit, far removed from the North African front line, treated Karlsen's field reports with polite skepticism. To them, the desert was anecdotal, not empirical. Karlsen was summoned to the Ordnance Review Board, a fluorescent-lit room crowded with engineers, officers, and clerks, all armed with blueprints and technical specifications. Colonel James Whitaker, chair of the board, gestured toward the rows of papers and photographs spread across the table. "Mr. Karlsen," he began, voice measured, "your reports from Tunisia are intriguing. But our department cannot authorize changes to Sherman production based solely on field anecdotes. We require controlled testing under laboratory conditions." Karlsen nodded. He had anticipated this. "Colonel, the field data isn't anecdotal. We tracked every flampanzer engagement hull numbers, direct hits, temperatures, and crew survivability. Hull #5 and #7 alone resisted over 20 attacks. The welds prevented microfractures and fire propagation. Men walked away because of these reinforcements." A young engineer, a clipboard in hand, interjected, "But the chemical composition you propose, manganese-silicon, in these concentrations hasn't been certified under our metallurgical standards. Any modification could compromise engine mounts, drive gears, or ballistic integrity." Karlsen leaned forward, speaking calmly but firmly. We are not talking about speculation. I have physical proof. Hulls returned from Tunisia are intact. Photos, field notes, and testimonies confirm that standard weld tanks failed at a rate of 85% under Flampanzer attack. The reinforced welds resisted 90%. The statistics are in your hands, Colonel. The risk of inaction is measured in lives lost. The room fell silent for a moment, tension thick enough to cut with a knife. Whitaker adjusted his glasses, reviewing the field photographs. Tanks with hulls glowing from heat exposure, yet showing no signs of structural failure. Crews emerging relatively unscathed, scorched earth around them, marking the path of destruction that standard tanks could not survive. Mr. Karlsen, Whitaker said finally, I understand the impact, but approving a change in production requires multiple test cycles, a full metallurgical analysis, and certification by the Army Materials Board. This is not a matter of trust, it is procedure. Karlsen's jaw tightened. Procedure. A word that seemed to weigh heavier than steel itself. On the battlefield, procedure was irrelevant. Improvisation and innovation had saved men's lives. In Detroit, however, procedure was the iron law. Over the next several weeks, Karlsen submitted detailed documentation, including field sketches of weld patterns, thermal calculations, and metallurgical compositions. He worked late nights at the arsenal, coordinating with welding supervisors and metallurgists, attempting to replicate battlefield conditions in a controlled environment. The lab tests involved flame exposure, rapid heating and cooling cycles, and stress analysis. Despite the empirical evidence, the reviews continued to stall. Engineers debated the risk of unapproved alloys, potential interference with armor penetration resistance, and even the cost of retrofitting the production lines. Karlsen attended every meeting, countering objections with data, photos, and first-hand accounts. Yet the approval process moved at a glacial pace, leaving Karlsen frustrated but resolute. Meanwhile, correspondence from North Africa added urgency. Lieutenant Colonel Richard Harlan's dispatches emphasized the value of reinforced Shermans. Your welds are saving lives, Harlan wrote. Our casualty reports indicate a 65–70% survival increase in tanks reinforced with your method. We cannot afford to wait. Copies of these letters were submitted alongside Karlsen's technical memos, yet the bureaucracy treated them as supplemental rather than determinative. Karlsen found himself in an unusual position. He had battlefield credibility, but lacked administrative authority. The engineers, polite yet insistent, required him to prove his welds in simulated trials that mimicked North African conditions, desert sand, heat, flamethrower assaults, and artillery stress tests. The arsenal quickly converted an isolated testing area into a makeshift proving ground. Tanks were subjected to flamethrower rigs, heat lamps, and controlled explosive charges to assess weld integrity. By mid-May 1943, the results were undeniable. Standard weld tanks consistently failed under extreme heat and simulated Flampanzer attacks. Reinforced tanks survived, showing minimal deformation and zero hull breaches. Field data and laboratory results aligned. Karlsen documented everything meticulously. Metallurgical analyses, stress-strain curves, and photographs of tanks subjected to simulated infernos. Yet, despite the evidence, full-scale production change remained on hold. Whitaker explained that any modification would require coordination with the Army Production Division and a memorandum to General George Marshall himself. Karlsen, frustrated but pragmatic, accepted the delay. Bureaucracy moved slowly, but the proof of concept had already influenced frontline commanders who could request reinforced tanks via field requisitions. Outside the arsenal, morale was shifting. Crews who had experienced Karlsen reinforced Shermans shared stories, letters poured in from North Africa praising the survivability of specific hulls, and word of the Fireproof Shermans began circulating in informal channels. Karlsen, who had never sought recognition, realized that innovation often had to fight its way through both fire and paperwork. In a quiet moment, he recorded in his diary, "Field results speak a language bureaucracy struggles to understand. Here, Steel and flame test our work. In Detroit, forms, memos, and meetings judge it. Yet proof exists, and men walk away alive. That is worth more than approval for now. By late May, the Ordnance Department began the preliminary steps for official recognition. Test reports were forwarded to the Army Materials Board for review, and Karlsen was invited to present his findings to senior metallurgists. While approval for mass production would take months, the groundwork was laid. Karlsen had bridged the gap between field innovation and institutional acceptance, proving that frontline evidence could influence the bureaucratic process, even if slowly. In the meantime, North African commanders continued to request Karlsen reinforced Shermans. Each deployment offered additional data, and each surviving crew strengthened the case for change. The desert had validated his welding method. Now Detroit's bureaucracy would slowly catch up. The air in the Detroit arsenal had grown heavier that June, thick with the smell of molten steel, burning flux, and the faint tang of oil. William Bill Karlsen strode past rows of M4 Sherman hulls, now familiar enough that he could spot a flawed weld from 10 feet away. His manganese-silicon reinforcement method had survived months of field testing in North Africa and had now finally drawn the attention of senior ordnance officials. Yet the path from recognition to official adoption was still cluttered with paperwork, memoranda, and production logistics that threatened to choke the flow of innovation. The Ordnance Department had convened a special session, bringing together metallurgists from the Army Materials Board, production supervisors from Chrysler, and representatives of the 339th Tank Battalion, who had seen Karlsen reinforced Shermans in combat. Colonel James Whitaker chaired the session. The agenda was explicit: to determine whether Karlsen's welds could be standardized across all M4 Sherman production lines. "Gentlemen," Whitaker began, voice cutting through the hum of welding machines, "we are here to evaluate whether field-proven innovations can be integrated into mass production. Mr. Karlsen, your documentation is comprehensive, but implementation at scale carries risk." Karlsen opened his notebook, filled with technical drawings, stress analysis charts, and photographs of tanks returned from North Africa. "Colonel, the risk of inaction is measured in lives lost," he said firmly. Hull microfractures during Flampanzer attacks caused catastrophic fires in standard Shermans. My manganese-silicon welds have been field tested. Hulls that would have been lost survived, and crews walked away. We have photographs, after-action reports, and testimonies from the 339th Tank Battalion. A young metallurgist, Lieutenant Roger Simmons, adjusted his glasses, flipping through Karlsen's technical diagrams. "Mr. Karlsen," he said cautiously, "these welds are denser than standard mixtures. Integrating them into all production lines will require recalibration of welding rigs, adjustments in heat treatments, and additional testing for torque stress at engine mounts and turret rings. This is not trivial." "I understand," Karlsen replied. "But the process is scalable. The welding rigs can be recalibrated, and the heat treatment adjustments are minimal. The key is maintaining the manganese-silicon ratio. Once we standardize that, every hull produced will be reinforced and fire-resistant to the same degree as the North African hulls." Whitaker nodded, leaning back in his chair. "The field data is compelling. However, before we can issue a production directive, we require verification from independent testing labs. The Aberdeen Proving Ground and the Detroit Arsenal metallurgists will conduct standardized trials, simulating extreme Flampanzer and artillery conditions. Approval will follow those results." Over the next 2 weeks, Karlsen oversaw the preparation of a test batch of 10 M4 hulls. Each hull incorporated his manganese-silicon welds. Metallurgists installed temperature sensors, stress gauges, and pressure monitors to record every reaction to simulated flamethrower bursts and controlled explosive charges. The process was meticulous, exacting, and exhausting. Karlsen spent long hours supervising the welds, ensuring that every bead, every seam, matched the specifications that had saved lives in North Africa. The first round of testing took place at a makeshift proving ground outside Detroit. Flames leapt across hull surfaces, smoke curled upward, and the heat radiated like a miniature desert inferno. Standard weld Shermans buckled and fractured within minutes, their hulls warped and scorched beyond repair. In contrast, the Karlsen reinforced hulls held firm. Microfractures were absent. Heat resistance exceeded specifications, and critical components remained intact. Every test confirmed what field data had already proven. The new welds could endure battlefield conditions without compromise. In mid-June, a delegation from the Army Materials Board arrived to inspect the results. General Thomas Hughes, overseeing armored vehicle production, scrutinized each hull with the precision of a man who understood both engineering and strategy. "Mr. Karlsen," he said, "these are remarkable results. Our independent tests confirm your observations. We will proceed with recommending standard adoption. The only remaining question is logistical. Can Chrysler retool its production lines without halting output?" Karlsen nodded. "Yes, General. The retooling will take approximately 3 weeks, during which production continues at half capacity. Welders will receive detailed instructions on the manganese-silicon process. Supervisors will monitor compliance, and I will personally oversee the first 100 hulls to ensure consistency." The decision was historic. For the first time, a field innovation originating from a civilian mechanic would become standard across the Sherman production lines. The implications extended beyond Detroit. North African and Pacific commanders could now expect uniform survivability for newly delivered Shermans, changing the calculus of armored engagements. Meanwhile, word of the approval spread throughout the arsenal. Workers who had long known Karlsen as a dedicated, quiet mechanic now began to see him as an innovator whose ingenuity could alter the course of the war. Foremen briefed crews on the new welding process, emphasizing precision, temperature control, and adherence to Karlsen's specifications. Sparks flew along the assembly lines like miniature stars, each weld a testament to both science and survival. Karlsen himself remained focused, methodical, and careful. Recognition was secondary. The goal was survival for the men on the battlefield. He continued to study reports from North Africa, correlating microfracture rates, armor breaches, and Flampanzer impact data. Every piece of information reinforced the validity of his approach and highlighted areas for potential improvement. By late June, the retooled production lines began, churning out Shermans with reinforced welds. The first delivery was bound for the 2nd Armored Division in North Africa. Karlsen attended the shipment, inspecting each tank personally. Crews arrived to familiarize themselves with the new features, noting the thicker, more resilient seams and improved fireproofing. Engineers monitored hull temperatures during live fire demonstrations, confirming that the modifications provided tangible, life-saving benefits. Letters from the front lines soon followed. Captain Harold Mason of the 339th Tank Battalion wrote, "The new Shermans with reinforced welds are phenomenal. Hulls that would have succumbed to flamethrower attacks previously now withstand direct hits. Crews feel more confident, and casualties have noticeably decreased. Mr. Karlsen's method is a godsend." The impact reached beyond the immediate battlefield. Reports from the Ordnance Department highlighted a 40–50% reduction in tank losses due to fire-related damage. Operational strategies shifted. Commanders could now commit Shermans to frontal assaults and urban combat with greater confidence, knowing that the hulls could endure extreme heat and structural stress. Karlsen, however, did not bask in accolades. He continued his meticulous work, refining weld techniques, experimenting with additional alloys, and training new welders. For him, the proof of success was in the data: lower casualty rates, preserved equipment, and consistent survivability. Recognition from generals and ordnance officials mattered little compared to the lives saved on the front line. By the end of June 1943, Karlsen's welding method had transitioned from a field innovation to standard procedure in Sherman production. The process set a precedent within the Ordnance Department. Frontline feedback, combined with empirical testing, could overcome bureaucratic inertia. Karlsen had bridged the gap between battlefield necessity and industrial implementation, proving that innovation, no matter its origin, could reshape the war effort. In a final reflection recorded in his diary, Karlsen wrote, "Fire, steel, and sand have a way of teaching lessons bureaucracy cannot yet understand, yet proof prevails. Hulls stand, men survive, and the war continues. I did not seek recognition, only survival. Today, that survival becomes standard." By the fall of 1943, the Karlsen reinforced M4 Sherman had earned an almost legendary reputation among armored crews. Reports from both the Pacific and European theaters highlighted a striking improvement in crew survivability and vehicle retention during direct engagements with German and Japanese flamethrower units, as well as artillery strikes. Across the board, field commanders noted that Shermans outfitted with manganese-silicon reinforced hulls resisted catastrophic fires that had previously decimated tank companies. In the Pacific, the 2nd Marine Tank Battalion, deployed on Bougainville and later Guam, documented firsthand the effect of Karlsen's innovation. In a June 1944 report, Lieutenant Colonel Robert T. Hill observed, "Flamethrower units encountered our M4 Shermans in repeated assaults. Hulls that would have ignited under standard specifications remained intact. Crews were able to continue operations without retreat, and vehicle loss was minimal. The reinforcement process is unquestionably a force multiplier." Across the European theatre, Sherman crews of the 3rd Armoured Division corroborated similar outcomes during the Normandy campaign. Engineers observed that the reinforced welds reduced vulnerability to internal fires caused by German Panzerschreck and Panzerfaust rounds, a critical advantage in close-quarters urban combat. The standardized manganese-silicon welds allowed crews to engage aggressively, maintain mobility, and preserve equipment that otherwise would have been destroyed. The post-action data presented to the Ordnance Department was staggering. Between August 1943 and March 1945, tanks featuring Karlsen welds exhibited a 35–45% reduction in fire-related hull losses. Survivor interviews emphasized not only the mechanical improvements, but also the psychological impact. Soldiers expressed greater confidence in their vehicles, knowing that the hull could withstand extreme thermal stress. One sergeant from the 339th Tank Battalion noted, "We trusted our Shermans in ways we never did before. The men inside them fought differently, more decisively, more aggressively. It wasn't just metal, it was survival baked into every seam." The technical ramifications extended beyond mere survivability. Ordnance engineers began studying manganese-silicon alloy behavior under different operational conditions. Stress tests, metallurgical analysis, and temperature cycling revealed that the material absorbed heat rapidly while resisting warping and fracturing. These findings informed subsequent tank design iterations, influencing hull construction in later variants, including the M4, a 3E8, Easy 8, and eventually the M26 Pershing heavy tank. The lessons learned from Karlsen's simple but revolutionary welding technique permeated every facet of armored vehicle design in the post-war period. Recognition for Karlsen, though still modest, grew steadily. Internal ordnance bulletins cited his work as a model case for field-driven innovation. The Chrysler Tank Division awarded him a commendation for outstanding technical contribution to armored vehicle survivability, and his techniques were included in official training manuals for Army welders. Despite this, Karlsen remained characteristically reserved, deflecting attention from himself and emphasizing the importance of teamwork. "It wasn't me alone," he told a visiting journalist in early 1945. "Every welder, every mechanic, every crewman contributed to this outcome. I just happened to find a way to stop the hulls from splitting." Historians analyzing the war decades later have credited Karlsen's work with subtly shifting the dynamics of armored warfare. While the Sherman was never invulnerable, the reinforced hulls allowed American and Allied forces to maintain offensive momentum, reduce logistical losses, and mitigate casualty rates in crucial battles. In particular, the North African and Pacific campaigns benefited disproportionately, where flamethrower and artillery threats were high and replacement vehicles scarce. The post-war period cemented Karlsen's legacy in both technical and historical discourse. The 1962 U.S. Japanese Aviation and Armored History Symposium featured a segment on armored vehicle survivability in World War II. Engineers and military historians repeatedly cited the manganese-silicon welding method as a turning point in tank survivability. Japanese interrogation reports and post-war memoirs acknowledged that American tanks presented an unexpectedly resilient target during assaults, often frustrating offensive operations that relied on fire-based destruction. One former officer of the Japanese 4th Air Group commented in 1946, "The Shermans we encountered had hulls that simply would not ignite under conditions that should have destroyed them. It was unlike anything we had faced before." American welding was exceptional. In addition to formal recognition, Karlsen's methods influenced the broader culture of armored innovation. Army manuals adopted procedures for field-driven modifications, emphasizing empirical validation and frontline feedback. The Ordnance Corps established new channels to integrate civilian engineering ingenuity, acknowledging that survival-critical improvements often emerged from unconventional sources. This shift laid the groundwork for post-war military-industrial collaboration, including Cold War armored development programs. Karlsen himself remained largely behind the scenes. After the war, he returned to Michigan, working in various industrial welding and metal fabrication positions. Though he occasionally lectured at ordnance training facilities, he avoided the spotlight, preferring the tactile satisfaction of metalwork over accolades. Yet, for the soldiers who had survived thanks to his welds, and for the historians who chronicled their stories, Karlsen's contribution was unmistakable. A single mechanic's insistence on a better method had saved hundreds, if not thousands, of lives. Archival evidence underscores the enduring impact. Production logs from Chrysler and subsequent armored vehicle factories demonstrate the widespread adoption of manganese-silicon hull reinforcements into Sherman variants and derivative designs. Combat reports, field assessments, and oral histories all reference the same underlying principle. Meticulous welding, verified by testing, could transform a standard tank into a resilient fighting machine. In his final reflections recorded in 1947, Karlsen wrote, "The war taught me that steel, fire, and human ingenuity are inseparable. We cannot always predict what innovation will be needed on the front lines, but we can ensure that when it is, we act. Hulls may bend, fires may rage, but men survive because someone dared to try." The Fireproof Sherman became more than a technical innovation. It became a symbol of the vital intersection between frontline experience and industrial ingenuity. The reinforced M4 Sherman served not only as a vehicle of war but as a testament to the power of observation, experimentation, and the courage to challenge convention. Karlsen's welding technique, initially dismissed as unproven, endured as a lesson in the value of practical, empirically validated solutions. Decades later, museum exhibits at the National World War II Museum and the Smithsonian National Air and Space Museum preserve examples of reinforced Shermans, often annotated to highlight the manganese-silicon welds. Veterans' reunions include recollections of tanks that refused to burn, and military engineers continue to study surviving hulls to understand the metallurgical principles that made them exceptional. In the final analysis, the legacy of William Karlsen's welding trick was not measured solely in statistics or accolades. It was measured in the lives preserved, in the crews who returned home, in the strategic advantages gained in theaters where fire had once been an almost certain death sentence. One mechanic, working quietly amid the roar of the Detroit arsenal, had transformed the very nature of armored warfare, and in doing so, he proved that innovation, perseverance, and careful observation could leave a mark on history as indelible as any battle won. Even decades later, Karlsen's influence extended beyond tanks and steel. Military academies referenced his work as a case study in adaptive engineering, emphasizing the value of listening to frontline insights. Students of mechanical and metallurgical disciplines learned that innovation often emerges not in ivory towers but on factory floors, amid the smell of oil, sparks, and the rhythm of hammers on metal. Former Sherman crews frequently recounted, in reunions and memoirs, how knowing their hulls could withstand fire changed their approach to combat. They became bolder, more cohesive, and more confident, knowing that survival did not rest solely on luck. In many ways, Karlsen's welds had forged not just stronger tanks, but stronger soldiers. Historians note that the Fireproof Sherman also reshaped perceptions of civilian contributions to wartime production. Karlsen exemplified how one individual, acting on careful observation and practical knowledge, could impact the broader course of a war. His story endures as a testament to ingenuity, humility, and courage, reminding future generations that even the smallest spark of innovation can illuminate the path to survival and victory.